Hello, this is Mrs. Dehn-Brastad, and today we're going to go over how to do Chapter 2, Section 1. And Chapter 2 is all about proof and how to prove that things are true. And we're going to first start talking about inductive reasoning to make conjectures, and then we'll move on to deductive reasoning in a section or two. So we're going to begin with a warm-up. You should know these terms from Chapter 1. All the stuff you learn in Chapter 1, all those tons of vocabulary words and those postulates, you need to know that for the rest of the book. So if you didn't throw your notes away, don't. Keep them, have them handy. You're going to be learning or using that material that you learned a lot. So number 1, points. Blank points are points that lie in the same plane. You should know what that answer is. Number 2, some other kind of points are points that lie in the same plane. And number 3, the sum of the measures of two, what kind of angles is 90 degrees? So hopefully you know the answers. Number 1 is collinear points, number 2 is coplanar, and number 3 is complementary. Our objectives for this lesson are 2 of them. One is to use inductive reasoning to identify patterns and make conjectures, and the second is to find counterexamples to disprove conjectures. Not very much vocabulary in this chapter. In this section, we need to know what inductive reasoning is, a conjecture, and a counterexample. All right, we're going to start off with looking for a pattern. Inductive reasoning is all about looking for a pattern and figuring out what would be the next item. So if we go January, March, May, what is the pattern? Let's see. The pattern is that we are going from January, but we don't put February in there. And then we go to March, and then we don't put April in there, and we go to May. So it looks like we're going every other month. So we're not going to put June in there, but we would put in July. Okay, how about this pattern? Looks pretty familiar. 7, 14, 21, 28. Looks to me like this would be 7 times 1, this would be 7 times 2, this would be 7 times 3, or maybe you notice that you'll add 7 each time. So you can figure out that the next number would be 35, because you can either just keep adding 7, or you could take 7 times 4 is 28, 7 times 5 is 35. Okay, look at this pattern. I put red dots at the point of the triangle that I want to look at. So the first one, the point is up. The second one, that red dot is pointing to the left. Then the red dot is pointing down. What will my triangle look like next? I went up, I went left, I went down. So if I just continue that pattern, I will probably go to the right next. It says that every time the figure is rotating 90 degrees counterclockwise. So the next figure would have that triangle with a little red dot in the point, just to kind of keep straight which vertex we're talking about. Okay, in this one, we have numbers again, but this time we have decimal numbers. So we have 4 tenths, often read as 0.4. We have 4 hundredths, often read as 0.04, and 4 tenths, hundredths, thousandths, which is usually read 0.004. The next item in the pattern is going to be that we need to add 1 more 0 after the decimal point. So it should be 0.0004, which is our tenths, hundreds, thousandths, 10,000ths spot. All right, here's our first vocabulary word. When several examples form a pattern and you assume the pattern will continue, that's inductive reasoning. The definition of inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. You may use inductive reasoning to draw a conclusion from a pattern. So inductive reasoning is all about looking at specific cases and patterns and examples. Okay, that's inductive reasoning. A statement you believe to be true based on inductive reasoning is called a conjecture. A conjecture is like your best guess of what you think will happen. And we believe it to be true because of looking at patterns and examples in specific cases. All right, let's see if we can figure out this conjecture. We have to make a conjecture. The sum of two positive numbers. Well, we have to make our conjecture based on examples or patterns or specific cases. So let's make some up. The sum of two positive numbers. Pick any two positive numbers. Sum means to add. So add any two positive numbers up. Well, there's one example. It's 5. I don't think that it's always going to be 5. Let's pick another positive number and add it to another positive number, and this time I get 20. How about 1,000 added to 9? I get 1,009. What is there about all of these sums, 5, 1,009, 20, is there anything that I could say is always true about them? Here, they did some with decimals too. I probably should have done that. All of these numbers are positive. When I add two positive numbers together, I always get a positive sum. I get a positive answer. So my conjecture could be that the sum of two positive numbers is positive. Now, I'm not proving that to be true. I'm just using inductive reasoning to make a conjecture that I think that that's true. It seems reasonable. Okay, let's do another one. The number of lines formed by 4 points, no 3 of which are collinear. That's a funny way to phrase it, isn't it? So if no 3 are which, that means 2 can be collinear. So like you could have that. So if you have 4 points, I don't know, I guess you could have them like that, right? No 3 are collinear. They want to know how many lines could you form. So I could form one line here, and I could form one line here, that's 2, and another line here, that's 3, and that's 4. But I could also connect this point to this one, that'd be 5, and this one would be 6. So it seems like I got 6 for this. Maybe if I drew a different, my points I'll arrange differently. Maybe I'm going to try another example. Let's do it where they're not so like nicely lined up. There. Oh no, that's 3 collinear, so that one's not a good point. How about way up here? There, I don't have any 3 collinear points. So now I'm going to connect them, and I'm going to count how many lines I could connect these with. So here's 1 line, 2 lines, 3 lines, 4 lines. That was a wavy line. And then I could go way up here, that's 5, and that would be 6 again. So my conjecture is going to be that the number of lines formed by 4 points, no 3 of which are collinear, is 6. All right, try this one. So what you're going to do to make a conjecture is you're going to try some examples, some samples, look for a pattern, and then see if you can fill in the blank there. So pause your video, do that, and then come back and check your work. So if you're back, I'm going to go ahead and try some. Oh, it says product. That should be a times sign, not sum, product. So 1 times 5 is 5. 7 times 9 is 63. 11 times 3 is 33. So that looks like the product of 2 odd numbers is always going to be odd. Okay, so that's what you should have filled it in with. There's probably other conjectures you could come up with, but that one makes a lot of sense. Okay, here's an example using a word problem using some biology here. The cloud of water leaving a whale's blowhole when it exhales is called its blow. A biologist observed blue whale blows of 25, 29, 27, and 24 feet. I'm going to make a little table of this. All right, so 25, 29, 27, and 24. So it's a good idea often to make a table. Another biologist recorded, so this was the blue whale. Another biologist recorded humpback whales, and their blows were different. So I'm going to use red for the humpback whales. And their blows were 8, 7, 8, and 9. And these were the humpbacks. So look at these numbers and see if you can find a pattern or if there's any kind of a conjecture that you can make based on the data. There's more than one answer for this. For example, maybe, there's their nicer, neater table. Maybe you just figured out that the second one here, the height of a blue whale's blow is greater than a humpback whale's blow. See, here's the humpbacks, 8, 7, 8, 9. clearly the height of the blue whales are bigger. They're all bigger. So your conjecture might just be that the height of the blue whales is greater than the height of the humpback whaleblows. But you might have got more specific and said, it's almost times 3. If I took 8 times 3, it's 24, which is close to that. And 7 times 3, well, that's only 21. That one's kind of fails there. This one times 3 would be 24, and 9 times 3. So it doesn't completely hold, but you could say it's about 3 times greater. It's an approximate. Or maybe you would say that the height of the blue whales, or that the height of the humpback whales is about 1/3 as big. So you can get specific with your conjectures, or you can get just kind of general. Okay, here's one for you to try. And you can, again, you're going to make a conjecture. You can be very general about your conjecture, or you can get real specific. It's up to you, as long as it's accurate and true. So we have some length of females whales, and then we have some lengths of male whales. And it doesn't say it in the data or in the description, but these are pairs of whales, like a male-female pair. All right, so let's see. What kind of a... if I was going to make a conjecture about this, the males are just a little bit smaller. In every case, let's see, this one's smaller, male smaller, male smaller, male smaller, male smaller, male. Oh, all of them except for one. In the last one, the female's 47 and the male's 48. Most of the time, I would say that the males were smaller than the females. So that could be a conjecture. However, it would also be a reasonable conjecture to say that male and female whales are pretty close to the same length. There only was a big difference right here. In most of them, the lengths of each of them was pretty similar. All right, if you want to prove that a conjecture is true, you have to prove it's true all of the time, which is really hard to do with inductive reasoning because it means you would have to look for every single instance or case or example of that. So it's hard to prove a conjecture is true. But to prove a conjecture false, it's not so bad. All you have to do is find one example in which it's false, in which it's not true. That's called a counterexample. A counterexample is the one instance that makes the conjecture false. And that's all we have to find in order to prove that it's false. Your counterexample can be a drawing, a statement, or a number that shows that your conjecture is not true. So here's the steps that we do for inductive reasoning. You look for a pattern, you make a conjecture, and then you luckily find a counterexample, or unluckily prove the conjecture using algebra or geometry or logic, deductive reasoning. You can't really prove it's true by inductive reasoning, but we can make a conjecture and we might be able to find a counterexample. All right, so let's find a counterexample. That's what you're going to be doing this section. This section will not ask you to prove any conjectures. All right, so we are going to show that the conjecture is false by finding a counterexample. So we can't write that it's true. It's not true. It's false. We know that it's false. All we have to do is find a counterexample. For every integer n cubed is positive. Integers, just as a quick reminder, those are the natural numbers, 1, 2, 3, 4, and so on, plus 0, plus the negatives, the opposites of the natural numbers. And it continues forever in both directions. So we have to find a time that this would not be true. So let's try it with a positive number 2. If n is 2, 2 cubed is 8. Well, that's true. It is positive. So that's not a counterexample because it's true. If I try it with any of my positive numbers, it's going to be true conjecture. But if I try it with a negative, let's see, that would be negative 3 to the third power. So that'd be negative 3 times negative 3, which is 9, times negative 3 is negative 27. Negative 27 is not positive. So my counterexample is negative 3. It doesn't work for negative 3. That's my counterexample. You don't have to find more than one. You only need one of them. they tried it with 1, and then they tried it also with -3, and they got the same thing. That would be false. Okay, how about this one? Show that the conjecture is false by finding a counterexample. Two complementary angles are not congruent. Complementary, review, is that they would add up to be 90 degrees. Two angles that add together to be 90 degrees. So you could have two angles that touch each other, like you could have 30 and 60 adjacent angles that are complementary, or you could have two separate angles that add together to be 90 degrees. 40 and 50, not to scale. Is there any that would be congruent? Can you have 90 be made up of two angles that are the same? Well, sure. What about 45 and 45? That's your counterexample. 45 degrees is your counterexample. Okay, with this example, we are going to show that it's false by finding a counterexample. The ones with tables are really easy. It says the monthly high temperature in Abilene is never below 90 degrees for 2 months in a row. Never below 90 degrees. All we have to do is find where it is below 90 degrees. I'm going to start at this end to make it trickier. This is below 90 degrees, but it has to be 2 months in a row, and this one's not. So keep going. Here, this is below 90 degrees, and this one's below 90 degrees. Right here, I've got 2 months in a row where they are below 90 degrees. So the conjecture is false because January and February are both below 90 degrees. I forgot and left my artwork on here from when I tried this video before. In this one, we're supposed to find a counterexample for any real number x, and I can't erase it, so you'll just have to look at my notes here. For any real number x, x squared is greater than x. So I did it with 2. I tried x is 2. 2 squared is 4. 4 is greater than 2, so it works there. I did it with -3. -3 squared is 9. 9 is greater than -3. That one works. But then I tried it with a fraction. You could try it with a decimal too. 1/2 squared is 1/4 because you take 1/2 times 1/2. And 2 times 2 is 4, and 1 times 1 is 1. So 1/4, is that greater than a half? If you have 1/4 of a pi, is that greater than 1/2 of a pi? No. So this one is false. So my counterexample is a fraction, 1/2, or you could try it with other fractions as well. And it won't work. So then you found your counterexample. Okay, here's one. It says, show that the counterexample is false by finding a counterexample. Supplementary angles are adjacent. So I drew supplementary angles that are adjacent. Yep, that makes it the conjecture true, so that's not a counterexample. In order to make it be a counterexample, it has to be false. So what if I just drew two angles that weren't touching each other? They're not adjacent, they don't share a side. That's a counterexample. That's one where you just had to draw a picture. You don't even have to use any words on that one. And in this example, again, I've got my notes on here, but it says, show that the counterexample is false by finding a counterexample. The radius of every planet in the solar system is less than 50,000. Now here's a tricky thing. They don't give us the radii, they give us the diameters. So we would have to divide each of these by 2. If you divide this by 2, it's certainly less than 50,000. If you divide that by 2, it's less than 50,000. The only ones that you divide by 2 and you get less than 50,000 would be the Jupiter or Saturn. If you divide those by 2, it would be greater than 50,000. So one of our counterexamples is Jupiter. Another counterexample is Saturn. You only need one, but there happens to be 2 on that chart. All right, if you want to do the lesson quiz, I know the bottom is cut off slightly, but you can pause it and check. You don't have to. You're ready to do your assignment. And then if you are wanting to check your work, then pause your video, do these problems, and then come back and check it. I'm going to rewrite number 6 here. Okay, well the answers are, number 1 would be 0.0007. Number 2 would be an arrow pointing up. Number 3 is true by, it's a rule. So you can prove things are true by, this is a rule in algebra. It's a property that a negative divided by a negative is positive. Every prime number is odd. Prime numbers are numbers that are only divisible by 1 in themselves. The first one is actually 2, and then it's 3, and then it's 5, and then it's 7. And 2 is an even number. So 2 is prime and it's even, so it's not odd, so that's false. That's our counterexample. Number 2, two supplementary angles are not congruent. Well, what about 90 and 90? They're supplementary and congruent. And the last one, the square of an odd integer is odd. And the square of an odd integer. So if you take 3 and you square it, that's 9. You can't really prove this is true, but if you do as many odd integers and square them as you can, we will see that they're all odd. We're not going to prove it, but it looks true. And that is the end of our lesson. Thank you very much, and if you have any questions while you do the assignment, please let me know. Thank you.